Good day, I'm Dr. T and welcome to my office. So today I would like to jump into the wonderful world of heat and kind of round out our discussion of energy. In doing so, I need to kind of discuss a little bit of what heat is not and some of the topics that it relates to. Okay, so for starters, heat is not going to be energy, but the flow of energy. So if we are going to compare it to what we've already learned, work is going to be the close comparison. In fact, we can describe the change in energy as being the sum of the heat and the work involved in a particular situation. I should point out that more or less I have not been too considerate with signs on the heat and work so far, but I should point out what the signs mean. When we're talking about energy, we're talking about the internal energy, so all the potential energy within the system, so whatever we're talking about. Generally speaking, we don't talk about this in terms of absolute amounts of energy because the mathematical operations in order to calculate every possible form of energy going on within a system, if that system is more than a few dozen atoms, is prohibitively hard to do to the point of absolute impossibility. Effectively, with every atom you add to the system, it exponentially increases the complexity of the equations involved. And after a dozen or two atoms, that gets a lot, let alone anything you have the ability to, see. So generally speaking, we talk about the change in internal energy. If energy is leaving the system, presumably going into the surroundings, because it doesn't just go away, but if energy is leaving the system, then your change in energy will be negative. Your sign of work potentially is negative if the energy is leaving by the system doing work on the surroundings, and or your heat is going to be negative because the system is exporting heat to the surroundings. In this case, we would call this exothermic, by the way. Side note, nothing says the work and the heat have to have the same sign. The work could be positive, the heat could be negative, it's just the work is not as big a number as the heat, so the sum would still be negative. Going the opposite direction, the change in energy could be positive. This means that energy is going from the surroundings into the system. And this could be coming in the form of work or heat, in which case, once again, those would be positive. Or one would be positive, one would be negative in case we're exchanging one for the other. So we've got these numbers. I'm not going to focus on the sign. Quite often when we are dealing with the flow of energy, when we're actually running the calculations, we might be particularly focused on the sign change, but quite often we know which way it's going. We'll just make sure the signs line up when we're done with the equation. So there's a lot of double checking to make sure the math is actually describing what it's supposed to be describing here and fixing it if it's not. Now, we've got this idea of heat. Now, how is heat not the same as energy? Also, why is it a Q? I will start with the impossible question first. Heat is given the symbol of Q in these equations because basically in the 19th century, some German researchers said, let's call heat Q. And no one bothered to ask why Q until they were dead, in which case it was too late. So scientific historians have some ideas of why heat is labeled Q, but basically no one actually knows why Q was given for heat. Okay, so let's move on to how is heat different than work. Work is going to be accelerating atoms in an orderly fashion. Heat is going to be doing that in a disorderly fashion. See, all atoms are always moving at least a little bit. And so we can change the amount they're vibrating or bouncing around, and doing so is heat. If we're making them go faster, we're adding energy to the system, so the heat is positive. And if we're making them bounce around and taking some of their energy from their bouncing, so we take the energy and they're bouncing less, well, in that case, that is taking heat out. So that would be a negative Q. Okay, now let's juxtapose heat with the other thing that it pairs most closely with, and that is temperature. Heat and temperature are intimately related, but they are not the same thing. Okay, so temperature, if we're looking at this, this is one of those where it is a property of a thing. It's not the change in the thing, it's a property of that thing. And if we're looking at, there's several different models to describe temperature. One of the most straightforward, although somewhat simpler models, it's still good enough for most applications, is the idea that temperature is the average kinetic energy of the particles within the substance. Keep in mind, everything's wiggling. And so if we were to plot, this is known as a Boltzmann distribution, if we're able to plot a graph of what percentage or how many different particles had a specific kinetic energy, so this would be 1/2 their mass times their velocity squared, then we could plot that average kinetic energy, or we could plot the velocity if it's just one thing. So this particular graph is just doing oxygen. It's not shown there, but it's doing oxygen. And we could plot its velocity on the x-axis, and we can plot how many members of the population would be on the y-axis, and we kind of get effectively like a curvy histogram. Well, at low temperatures, in this case negative 100 Celsius, you get kind of a nice peak. You get these, there's not a true Gaussian distribution because it's you can't go less than no energy, but you can go really high. So it's got an uneven tailing, but you've got a Gaussian S distribution, so kind of a bell curve-ish. And it's fairly tall and thin, and it's kind of crammed in towards the slower speeds. If we heat it up a little bit, maybe to 20 degrees Celsius, it starts to spread out. You get a lower bell curve, but a wider bell curve. And then the peak of the bell curve, which is your average, is going to be a higher kinetic energy or a higher velocity. And then if we kick it up even hotter to, say, 600 Celsius, well, we can spread it out even more. Once again, the peak of the bell curve, the average moves even further. Temperature is a description, in many respects, of the average kinetic energy of the particles in the system. Heat is the flow of energy into or away from the system. So the two topics are related, as in, if I flow energy into the system by this chaotic motion, I'm going to raise the temperature. If I suck energy out, I'm going to lower the temperature. But the two things are not the same. They're intimately related, but they're not the same topics. Let's talk about some equations involving heat and temperature. Generally, this is kind of called a calorimetry equation or a specific heat equation. I'm only going to do one form of this equation, but we can modify it, do some algebra to kind of spice it up a bit. So the general form that I'm going to bring up is the idea that heat, so the amount of heat going into or out of the system, is going to be equal to the mass of the system. So how much we got here, because keep in mind we're dealing with kinetic energy going on and mass is a function of that, times CS. CS is the specific heat. And so this is for that particular substance, whatever's making up my system, how much energy does it actually take to raise it up a degree Celsius or a Kelvin? And I'll get into units of temperature here in a minute. You can do this in Fahrenheit, but usually we do degrees Celsius or Kelvin, which in this case are interchangeable. And so you got your specific heat, and then you've got your change in temperature. Basically, how much does it heat up? And so if I know the different properties, if I know all but one of them, then I can solve for each one. And keep in mind, change in temperature, delta T, that is the final temperature minus the initial. So where can we use this? Well, one, we can use this to do calculations. Well, how much heat would I need to heat something up, which could be incredibly valuable. Or likewise, how much heat is stored in something that's hot that I can give off by letting it cool down to a specific temperature. But also, looking at that specific heat gets particularly interesting. It's going to tell how responsive something is with its temperature increase with respect to the amount of energy we put in there. If we've got something where we only need to add a little bit of energy to really get the molecules bouncing around pretty quick, it's going to have a relatively low specific heat. Whereas if it takes a lot of energy just to get them up a little bit faster, that's going to have a much higher specific heat. This is a complicated series of equations that I'm not going to go into the factors that actually control the specific heat, but I do want to see a little bit of outcomes of this. And one of the classic ones is if you compare Yuma, Arizona with Savannah. The two cities are relatively similar latitudes, give or take a smidge. So they're getting about the same amount of energy from the sun. Yuma, Arizona, however, is the sunniest and one of the driest cities on Earth. I don't know if it's the driest city on Earth. I do know it is the sunniest city on Earth. There are sunnier places on Earth than Yuma. No one lives there. So it's got lots of sunshine, very little clouds, very little moisture. A lot of agriculture is done there, but all the water is pumped in via aqueducts. and various canals. So Yuma is in the middle of the Sonoran Desert. It's a desert, it's dry, there's not much water. Whereas Savannah is at the coast. In Georgia, there's lots of water. It's a very wet environment, lush vegetation in that area. Now, they're getting about the same amount of heat from the sun. So heat's coming in from the sun in the form of radiation. It's heating up the area. Water has a very, very high specific heat, whereas sand and rocks have a relatively low specific heat. Now, let's think about what we know about deserts. They get really hot in the day, and then they cool off heavily at night. That's definitely the case for Yuma. 120 in the sun? That's typical July or August. I should say 120 in the shade. If you're standing in the sun, it's going to get even hotter for you because you're taking that heat directly from the sun. By the way, dry heat with a breeze, 120 is still ridiculously hot, but if you're not moving and you're in the shade, it's hot, but it's not unbearably hot. Okay, it's hot. Whereas in Savannah, it's not going to get that hot. The humidity is through the roof, though, because there's lots of water there. So in Savannah, the temperature swing is going to be a lot less than that of Yuma, Arizona, because Savannah has lots and lots and lots and lots of water. You can see a slightly similar approach if you look at, say, San Diego, which is like right next door to Yuma. It's still in the desert, but it has that gigantic thing of water called the Pacific Ocean right next to it. So you get the general idea. High specific heat is going to mean you have to put in a lot of energy to heat that up. This is one of the reasons if you're heating up water on the stove, it takes forever to heat that pot of water up, whereas your cast iron skillet that's just about as heavy, that thing gets hot quick because specific heat of the metal is a lot less than specific heat of the water. Okay, one more equation for y'all before we jump into some more conceptual stuff, and that is if I do a change. So if I have a chemical reaction or a physical change, I'm doing some kind of change. Quite often, heat is involved. Energy is going to be given off or consumed in that change, and we describe that with a quantity called the enthalpy of. It'll be enthalpy of whatever that change is. And this is given the symbol delta H, and it'll have a little subscript describing what the change is. So delta H is delta H combustion. So COMB would be delta H combustion. So we're burning something. Delta H vape would be for vaporization. We're evaporating or boiling something. So it doesn't matter if it's chemical or physical, we're still going to give it the same kind of number. And this is experimentally determined. This is a constant for that particular change. And so you multiply that typically by the amount in moles. It could be by mass, but it's usually in moles, so read the fine print. And that will give you your heat for that particular change. I will caveat, if you're doing math, typically speaking, the calorimetry is in units of joules, where the enthalpy is usually given in units of kilojoules per amount. So once again, the specific heat would be joules per gram degree Celsius, whereas the enthalpy of would be kilograms per mole or kilograms per gram. Usually kilograms per mole, though. Which does mean you have to be careful. You got two different units of temperature going on over here. Generally speaking, changes are going to have big numbers here. There's a reason it's in kilojoules, not in joules. They're usually fairly large amounts. Okay, so we just covered a whole bunch of math. Let's look at some of the changes that we can be dealing with. The ones that are nice and those nice physical changes, fairly straightforward. And the first ones that come to mind are states of matter. So remember, everybody is wiggling constantly, but there's differences between wiggling. So we could be wiggling, but not really able to escape the intermolecular forces. So remember, molecules stick to each other. And if you're not wiggling too much, you're going to kind of get locked together. Maybe in a lattice as a crystal, maybe in an amorphous substance. They're going to kind of be locked together. So in this case, we're going to be a solid, and our atoms are going to kind of wiggle, and they're going to stay kind of input. Now, if we increase the temperature, then we can actually do one of two things. We could melt our solid or sublimate our solid. If we're going to melt, we're going to go in and become a liquid, where we're able to move past each other, but we still can't bounce around free. So the liquids are going to kind of slosh. You know what a liquid is. It fills the container up to a point. It doesn't fill the whole container, and it takes the shape of the container. Alternatively, we can skip the liquid and go straight to a gas with what's known as sublimation. So in this case, they're just bouncing around all over the place. The intermolecular forces have lost most all of their control. Not all of their control, but they're not grabbing on very well with these guys. So these guys are kind of bouncing all around. Now, of course, you can go in reverse. You know, liquid could go back to solid, that's freezing. The gas could go back to the solid in the form of deposition. So deposition is the opposite of sublimation. Now, of course, if I'm the liquid, I could go to the gas. And so this would be vaporization. So vaporization is the generic term including things such as boiling and evaporation, etc. So we're vaporizing into the gas, or we could be condensing back from the gas into the liquid. Now, there is one more state of matter. I don't have any cool GIFs downloaded from Wikipedia. Instead, for this one, just gonna have to let you use your imagination. This is the plasma. Plasma is one where this is so hot. It's a gas that is super hot to the point where the electrons are starting to get shucked off of the atoms. So you've got a bunch of cations and electrons just kind of as a gas. Going from a gas to a plasma is known as ionization, and going back is recombination. Now, those are your 4 classic states of matter. However, there's a couple other states of matter that kind of maybe need a mentioning because they're not really states of matter. This is the joy of language. We have things that are states of matter that they're not states of matter. They're things that we need to think about, but they're not one of the 4. These are kind of like the classic 4. There's some newer, advanced, exotic states of matter that get added to this set of 4. But there's a couple ones that are not nearly as exotic that are usually put in as kind of a subset. The first one I want to bring up is that of powders. Solids, if you grind them into fine powders, they're still very much a solid. They are a solid, 100%, but they start behaving a bit like liquids or potentially even gases if you poof them up. Because they have this huge surface area, their chemical property is going to be somewhat different because solids react on the surface. And you know what? They can flow. You take a pile of a powder and it's going to kind of flow out. The angle in which you can make your pile, the max angle, is called the angle of repose. If you try and go over that, it just flows away, kind of scenario. So with powders, especially if you're thinking in terms of safety, oh, they have their own unique safety problems, just because they're little tiny particles. The next one, I actually want to put up a graph. This is called a phase diagram. And this is a graph comparing pressure, which is how much the bouncing atoms are squishing in on each other on the y-axis, and temperature on the x-axis. Because this is one of those not a state, kind of state of matter things that show up when you do this plot. Okay, so at higher pressures, or really just about any pressure, but moderately high pressures and very low temperatures, you get solids. So there's kind of this region kind of from the origin up, but kind of hugging the y-axis that we call solids. Now, there's a line between that, kind of boundary it, and down on the bottom, kind of the mirror image of that, so high temperatures, low pressures, kind of going from the origin, hugging the bottom of this one, we've got ourselves the gases. Now, if you draw a line from the origin kind of coming up, it's going to Y. The left fork is going to continue on being the border between the solids. The right fork is going to be the border between the gases, but now all of a sudden there's somebody in between the 2 forks of this Y, and that is your liquids. So at kind of medium pressure, medium temperatures, you're going to get yourself some liquids. Where this Y branches off, we call that the triple point. And around there, you can, generally speaking, get both the solid, the liquid, and the gas relatively easily in the same environment if your temperature and pressure is close to your triple point. The temperature and pressure here on Earth is close to the triple point of water. That's why we have got ice, liquid water, and steam. Well, I should say water ice, liquid water, and steam. Yay! By the way, close is a relative term here, by the way. Now, the solid line kind of keeps going up, and it will wiggle back and forth. You can get different lattices going on in your solids, so different polymorphs. So you can have somewhat different narrative going on in your solids. It can get a little bit more complicated than it's usually shown in these. But there's an interesting feature. That liquid-gas line stops. It just abruptly stops at a point we call the critical point. At which point there is no more border between liquid and gas. The region that is going to be higher in pressure and higher in temperature than this critical point is what we call a supercritical fluid. Fluids are going to be anything that flows, so liquids and gases, as much as I want to call powders a fluid, they're a powder. Powders are still solids, but they're weird. But fluids are liquids and gases. When you're in this region that is higher temperature and pressure than this critical point, you're entering what we call supercritical fluids. They're not considered their own unique state of matter. I kind of think they should be in some respects, but they're not. However, they will have somewhat unique properties that are different than the gas of that particular substance or the liquid of that particular substance. And it'd be rather interesting. Also, you can go from a liquid to a supercritical fluid to a gas and never actually engage in a phase change. It's rather interesting. There's no distinct point where the phase changes. You just kind of slowly transition between the two. Now, on this phase diagram, plasma is not shown. That would just be really, really far for the temperature one. Usually these are not zoomed out far enough to start seeing plasmas in dealing with that. Interesting side note, by the way, gas and vapor are technically two different things, although usually we don't distinguish them. Gas is going to be if you are below the critical pressure, but above the critical temperature, whereas a vapor is going to be you are below the pressure to be a liquid, so you're below that liquid line, but your temperature is less than that of the critical point. And the idea here is that a vapor will transition back and forth with a liquid, and so you'll get this kind of equilibrium going on. And as you've seen that, humid day, you evaporate, things can all feel foggy kind of scenario. If it's a really humid day, you can definitely feel that transition going on. The last couple of topics in this part of the video before I move into the wonderful world of work and the flow of energy is looking at temperature. So if I look at temperature, remember that can be modeled as the average kinetic energy of my particles. Well, understanding that then means that there must therefore be a temperature where the average kinetic energy is essentially zero, because I could always go colder, but I can't have negative energy. Negative energy is not a thing. If energy, the total amount can't go negative. The change in energy can be negative, that just means it's leaving. But the total amount, that can't go negative. So there's a temperature by which I can't go less than. This is called absolute zero. Now, I will point out that our model describing temperature as the average kinetic energy kind of breaks down once we start getting close to absolute zero, and we'll start needing to use more advanced models for our definition of temperature. Likewise, if we only have a couple of atoms going on, that model particularly breaks down if it's a very, very simple system. There's just not enough for a good average. Now, if we want to measure temperature, we have, generally speaking, 4 options. The oldest of which is the Fahrenheit, and these are all named after people, by the way. So Fahrenheit, the guy sets up the Fahrenheit system, basically comes up with one of the first good thermometers. And the goal here is, roughly speaking, 0 degrees Fahrenheit. We're not entirely sure exactly why he picked these points, I should say. But roughly speaking, 0 degrees Fahrenheit is the freezing point of seawater, and 100 degrees Fahrenheit is a little bit higher than body temperature. It's probably the highest temperature that where he lives gets to. Celsius comes up just a smidge later, in which case the freezing point of pure water is used for the 0, and the boiling point is used for the 100-degree mark. In general, Fahrenheit for kind of a just day-to-day existing is not a bad unit. Celsius is a little bit easier to work with if you're not just thinking about room temperature. Now, both of these have an absolute scale counterpart where you use the same size units, but instead of starting their 0 point at the freezing point of either seawater or pure water or some arbitrary point, which is why we call them relative scales, then we'll start it at an absolute 0. So an absolute scale is going to use the same size tick marks, but the 0 point is going to be absolute 0. The absolute scale for Fahrenheit is ranking. Basically, no one uses ranking anymore. The counterpart for Celsius, which is the same size units as Celsius, is going to be Kelvin. This is the SI unit for temperature, is going to be the Kelvin. Side note, because they use the same size unit, if you're doing a delta T, you can use them interchangeably. If you're not, and you're actually using the actual temperature, then you convert from Celsius to Kelvin by adding 273.15 to your temperature in Celsius. This way you adjust between Kelvin and Celsius because absolute 0 in Celsius is negative 273.15. Okay, so let's talk a bit about heat flow. Okay, so let's talk about the heat flow. As heat is flowing into a system or flowing out of a system, we can get a couple of interesting things going on. For starters, the temperature is going to change, and we can do a heating or cooling curve. They're the same thing, it's just one's going up, one's going down, and they'll be the mirror image of each other. Now, if we wanted to go for kind of a long stretch, let's say we start out with some ice or from some steam, we're going to have some phase changes as we're going from ice to steam or steam to ice. As we are heating something up or cooling it down, you're going to watch the heat coming in or leaving, whichever way it's going, and then the temperature will be changing. We're going to use Q equals mass times specific heat times delta T, and that's going to calculate this particular change in temperature. So effectively, the specific heat is going to be the slope of this line. But if we are doing a phase change, well, in this case, we're going to have a straight line. Temperature doesn't change during a phase change. Now, you might have some hot spots and some cold spots, but the total temperature of your system shouldn't be changing during a phase change. This is actually fairly useful. This is why, say, ice is able to keep things at a relatively constant cold temperature. All the heat that's trying to heat up your food inside your ice chest is going into melting the ice. Once it melts the ice, then it can start warming up your food. Now, once again, there can be hot spots and cold spots, so your food could be a little bit warmer if you didn't pack it in the ice particularly good. Now, we're going to have these nice long lines, and they're going to be described by delta H. So the mass or moles times delta H, depending on which one your units happen to be in, that's going to describe the length of the line. If I want to figure out how much heat to go from one end to the other, I have to calculate it for each individual segment separately. Okay, so let's go ahead and talk about heat and work. Heat is always going to flow from hot to cold, at least always spontaneously flowing from hot to cold. Now, as it's flowing, we can use what's known as a heat engine. And the heat engine is going to exploit the physical properties of something, probably a gas. Good old steam engines are a classic example of a heat engine. But we're going to use the properties of something, probably a gas, in order to convert some of that heat into work. And so now I can convert that flow of heat, I can siphon some of that off and turn that into work. Now, if I talk about the engine efficiency, I'm in many respects describing what percentage of heat I can shuffle off to work. It's never going to be 100%. I'm always going to have some flow out. I can never be 100% efficient. And also, I can never get more work out than the amount of heat that I put in. The first law of thermodynamics is the conservation of energy. You can never get out more than what you put in. It's always going to be the same amount. The second law of thermodynamics is that the system is always going to increase in entropy, or it's always going to increase in chaos. Basically, you never get out in a usable fashion as much as you put in. So some of your heat's always going to go from hot to cold. You're never going to get more heat out than what you put in, and you're never going to get 100% efficiency, even if you would really very much like that. This is one of the reasons why, or the main reason why, perpetual motion machines just cannot exist, at least not in our reality. Okay, so we can exploit the mechanical and physical properties of something and extract some of the energy from the flow of heat going from hot to cold and turn that into work. We will slow down that flow of heat, by the way. So if we're also trying to cool something down, this will get in the way of cooling. There's a couple of great ideas like, we could say, take all that waste heat from data centers and turn that back into energy, except that it would make the data centers even hotter. And yeah, it's a great idea. It doesn't quite work out well. We still have the problem with data centers. Okay, so we can get work out. But remember, basically everything in physics is reversible. So we could put work in to our system and we could get the flow of heat to go in reverse. So we could, by using work, get heat to flow from a cold part to a hot part, thereby making the cold part colder and the hot part hotter. This is refrigeration or heat pumps. We use this all the time. It's a great technology, and if we're wanting to heat something up, we can put 1 unit of energy in the form of work, and we can get several, 3, 4, 5 units of energy in the form of heat being moved over to generate a nice large amount of heat. Some of our heat pump-based water heaters do this. Alternatively, if we just want to make something cold, we can put some energy in and we can make the cold side even colder, which is, how refrigeration and air conditioning works. Definitely quite helpful for us. Okay, the last part I want to talk about is how we get heat to actually flow. There are a couple of ways of getting heat to move. By the way, you will see this list change a bit. Most textbooks use 3 approaches. Some will go a little bit further. The first approach is that we can transfer heat by radiation. Basically, we can turn it into photons. Typically, we think of infrared, but it does not have to be infrared. Infrared just happens to do a particularly good job of doing this. So if something's hot, it's going to give off light, and then that light will impact other things, and it will warm them up. Radiation is nice in that it works through a vacuum. So all of our heat from the sun is coming in the form of radiation. However, radiation generally is the least efficient way of getting energy to flow. If you have seen any of the discussions of AI data centers in space, one of the narratives is cooling, because you would have to cool the things with radiators that radiate off using radiation. This is doable, but a pain. It's easier or more effective to get heat to flow using conduction. In this case, we have a solid material and the atoms are vibrating, and then they bump into the atoms that are next to them, and so on and so forth, and the heat travels through, typically speaking, a solid material. It conducts through the conductor. Now, if we can get some material nice and hot, so we can transfer a bunch of material into some matter, and we can just move that matter along in a process sometimes referred to as advection, then we can get the heat to move along in packets of material. Now, generally speaking, we don't really focus on that. We focus on a subset of this known as convection. So we're going to get the matter to move. We're going to put heat into matter. In this case, it is going to be a fluid, and we're going to use the force of gravity and its changing density in order to get it to move. See, keep in mind, the more they're bouncing around, the more space they're going to end up taking up. So as things get hotter and they bounce around more, they're going to expand. This is something we have to be careful with when building things. If I have a nice road or something and it gets warmer, it's actually going to expand. Years ago, I saw a sidewalk in Yuma, Arizona, which was long. I mean, very long. Went for a mile or so. It must have been poured in the winter. It makes sense. It's a lot cooler in Yuma in the winter. And in the summer, I was driving by, and it had buckled up, and there was one slab of sidewalk, probably 10 feet long, that was buckled up at a 45-degree angle, and another 10-foot long slab of sidewalk at another 45-degree angle. It expanded enough such that it had to buckle in order to go somewhere. It couldn't exist in its length in the footprint that it had. So we have to build into this idea of expansion into the stuff we create. You'll see expansion joints in bridges, those kind of like teeth things that you drive over. Those will expand and contract. You'll even see little rollers on the bridges for them to wiggle around as they expand and contract. Well, when fluids expand, they can flow. So that's not a problem, but as they expand, they have the same mass, but a slightly larger volume, so their density goes down. Well, if you're in a fluid, the thing with the most density, like the cold fluid, is going to be pulled down by gravity harder than the thing with less density, so it's going to float. As such, the hot fluid floats, the cold fluid sinks. If the heat is coming from the bottom, then the cold fluid that is now sunk is going to start heating up, and the hot fluid that's now on the top is going to start cooling off. And so now it's going to sink again, and we get this convection current. I should point out that convection currents usually aren't one big giant circle. Quite often we draw them as one big giant circle, and sometimes they can be one big giant circle, but quite often we get little pockets where you get these individual circulating cells. This is going to be important for weather, because weather is going to be heavily involved by these pockets of circulating cells, as well as things like ocean currents, the picture you can't see behind my head. So this idea of convection, we're going to move heat by moving matter, and we're going to do so with gravity. This means that in a microgravity environment, you don't get convection, which definitely means things like flames up in low Earth orbit don't really behave like you would think they would, because the convection is also how we power fire quite often. Fire heats up the air around it, it rises, fresh, cool air sinks and comes in, and you get this nice exchange. If you look at a traditional oil lamp, they are optimized to enhance the convection by encouraging this nice chimney that gives a much better convection by kind of forcing the air into nice channeling funnels. Because, of course, we can modify our convection. We also do what's called forced convection, where you put in fans, think a convection oven, to kind of enhance the process of convection. Okay, so with that said, have a wonderful day, and I will see you in future videos.